Well, I think soils have to be, as far as geological materials go, about as important as you can possibly get for the human beings, because without soils you would have no rooted land plants, and without rooted land plants you'd have no bottom for the land food chain, and if you don't have the bottom for the land food chain, you can't have anybody on top of it. So I think that it's really important. That's the only reason why we're here, is because of the existence of soils. So now, before I even get started in this topic, this is a science unto itself. We're talking about pedology. I mean, there are people who spend their lives studying soils, so the idea that I can get up here in maybe 1 or 2 lectures and teach you about soils is almost ludicrous. But that's not what I'm trying to do here. I think what I want to do, and I think I can do it, I want you to see what they are. I want you to see basically what seems to control the kind of soil that you get. I want you to see the basic composition of the soil, and really what I want you to see is how they do their thing. Okay, so and I think I can do that. So let's look at some definitions. Again, definitions really depend upon what it is you're trying to explain. But when I first took my first soils course, the definition that was given to me was that soil is that part of the regolith. Now let me stop right there. Regolith and soil are not the same. It's amazing how many students sort of confuse the two and look upon them as though they were. They are not. Soil is that part of the regolith down to the deepest penetration of plant roots. Now the regolith, you remember now, what that is simply that mixture of rock fragments and largely clay minerals now, that's the big component, and quartz and a little bit of iron oxide to give it color. That's the regolith. That's the material that accumulates above bedrock. Soil is that part down to the deepest penetration of plant roots. So for example, in the little diagram where I drew the plant roots only went partial of the way down to bedrock, the top part would be soil. Now all of it now, the whole thing is still regolith, but the top part would be soil. But if I were to draw the roots going all the way down to the bottom and maybe even into the bedrock, then all of the regolith would have been converted into soil. But note, they still are not the same. Regolith comes first. You have to have regolith before you can have soil. So that was the definition I learned. And the new one that's come out now in talking to my soil science friends, it says basically the same thing, but with a little proviso on the end. The new definition says, soil is that part of the regolith that supports plant life. Well, when you think about it, that's what I was saying. Wherever the roots go, that's where it's supporting plant life. So that's a pretty good part of the definition. But then they tack on a proviso on the end that's sort of interesting. It supports plant life out of doors. It has to be outside. Now, that brings up a little dilemma here. I mean, for example, I don't know about you, but we have all kinds of potted plants in our house, and they're growing in these pots. And this thing is, what is it growing in? What's in the pot that's feeding it? Well, you say, well, that's potting soil. I'm sorry, it can be soil because the plant's on the inside. But note, if you picked your pot up and took it out on the patio, now it becomes soil because it's outside. But then when you bring it back in again, you can't call it soil because it's not feeding it out of doors. So what is the stuff that's in your pot? Well, I would define the stuff that's in your pot on the inside is dirt. On the outside, it's soil. So that's my very unscientific definition and difference between soil and dirt. Dirt is soil brought into the house. That's what my mother used to say, as a matter of fact, you see. So anyway, there's your definition. Now, in terms of soils, there is one overriding feature or factor that determines what kind of soil you're going to get. Now, in this idea of kinds of soils, the new classification system, I believe he told me it came out in 1974 or something like that. There's something like 14,000 different kinds of soils. Most of them, a lot of them, little microenvironments and things like that. And obviously, we're not going to talk about any of those. But what I want to do is just to show you, for the United States, for example, what the basically different kinds of soils are. And the important thing to note is that the main controller over the kind of soil that you're going to get is the climate. Now remember what climate is. It's simply the combination of temperature and precipitation that exists over a large area for a long period of time. as opposed to weather, which is also temperature and precipitation, but that changes hourly, you see. The climate, the weather this morning is different than weather now, but the climate, you see, is within the region over long periods of time, probably geological periods of time. So we're going to look at the United States first. For example, if you look at the United States can be broken into a temperate, humid climate, a temperate, semi-arid climate, and a temperate, arid climate. Okay, so in other words, we're all temperate climates here. Temperate means we're talking about seasonal changes in all of those. So we have summer, spring, fall, and winter. Now, humid. What humid is by definition, it's any part of the country that gets more than 20 inches of precipitation a year. For example, if you look at a map of the United States and you locate the 100th meridian. Now, 100th meridian would be just west of the Mississippi River, sort of midway in Oklahoma and those states running north-south. That would be about the line of 20 inches of precipitation a year. From there eastward, you have greater than 20 inches of precipitation. So that would be the humid section of our country. For example, where I live in West Virginia, we're actually up now into the 40 inches of precipitation per year. And the highest in the east is actually down in the area of the Mississippi Delta, and they get over 60. So in other words, within the United States, in the east, the highest precipitation would be just over 60, but the whole area would be humid. Now, from that 100th meridian, that 20-inch precipitation line, almost everything to the west, the great area to the west, is semi-arid. Semi-arid would be 10 inches of precipitation to 20 inches of precipitation a year. And if you look at a map, that's what most of the western part of the United States is, except for two places. Obviously, the desert southwest. The arid region of the country, that would be less than 10 inches of precipitation. And of course, we're talking there Arizona, New Mexico, much of Utah, Nevada, some of Southern California. That would be our arid region. Now, the other exception to that semi-arid would be the very northwest. This is an interesting little trivia for you. If you go to the northwest, this would be now the very western portion of Oregon and Washington. The Olympic Mountains in particular. If you look at the Olympic Mountains within the continental United States now, they have the highest precipitation anywhere. They have over 200 inches of precipitation a year. If you ever go there, which I've been on field trips, it looks like a tropical rainforest. You got all this hanging moss and all these ferns all over the place because of the extreme high precipitation. And we won't get into why that's the case. So anyway, there's your sort of the climatic picture. Now, in terms of soil types, to talk about the greater than 20 inches of precipitation a year first. There are two soil types that the new classification has. One is called a spottisol. The other is called an altisol. Now, these are called the forest soils. Now, the significance of being forest. It turns out that the average tree requires more than 20 inches of precipitation a year to make it. In other words, think of a tree. You need an awful lot of water to feed all that sap throughout the entire tree to feed it. So unless you have at least 20 inches of precipitation a year, you're not going to have much in the way of tree growth. But if you do, you will. So the idea is, if you look at the United States, just about anything to the east, certainly of the Mississippi River, one of the dominant kinds of foliage are trees. Now, the interesting thing is that if we go back in time, and when I say back in time, before we showed up on the scene, when it was just the Native Americans here, and the Europeans haven't even thought about coming into this part of the world, this was the great eastern forest. It was all covered with forest. I have read some comments where all the fields that you see in the east that are now used for agriculture, they were never here then. They were made that way by the settlers coming in, chopping down the great eastern forest to convert it over to agriculture. So when you see the forest today, they don't look like the forest did then. So you have the great eastern forest. Now, the two kinds of soil, spottisol and altisol. When you think of the eastern part, not just the United States, but especially North America, the kinds of trees you have, well, once you get north, let's say, of upstate New York and somewhere around the Great Lakes region, and you head north, the dominant tree type are conifers. But we go south of that, it's largely the broadleaf trees, the hardwoods, things like oak and maple and things. Well, that has an effect upon the soil. The spottisols are those soils that develop under conifer cover, The altisols are those soils that develop under broadleaf cover. The difference between them, they're very, very close in composition, but the main difference chemically between them is that the spotosols are a little bit more acid. Now, some of you may have had that experience. If you think about the needles falling off pine trees or things like that, when they decompose, they produce acids. For example, hemlock, tannic acid, when they used to tan skins, for example, that's where they got the tannic acid that tanned the skins, was from the hemlock trees. So that's pretty much characteristic, I think. Now, I'm not a botanist again, but as I understand it, the decomposition of the conifer products gives you more acid. So that's the only difference between those two. Now, let's take the semi-arid. We're talking now 10 inches to 20 inches. The soil type is called a mollisol. The mollisol we're going to talk about in some detail. These would be the great interior soils of the world. These would be the great grassland soils of the world. And you'll see why they're grasslands when we get around to talking more about the composition of them. So that's the so-called mollisol. Now, when you get down into the desert Southwest, until this new classification scheme came onto the scene, this was a very difficult thing for the soils people. Because if you ever go into the desert, by definition, a soil was defined as that part of the regolith that supports plant life. Well, if you go into the desert, there are some plants there, but there's one over there, and there's one over there, and there's one behind you someplace. There's no plant cover, you see. There's no continuous plant cover. So you don't have the plant domination in the desert. What do you have in the desert is really nothing more than regolith all by itself. So there really is no soil, as we've been sort of alluding to. Well, you see, that was a real problem for the soils people until the new classification. But now they took care of that, because now they have the aridisol, the arid soil. And so that's what we have in the desert Southwest. So within the continental United States, then, we have the spotosol and the altisols greater than 20 inches of precipitation. We have the mollisols, which are 10 to 20, and then we have the iridisols. Now, there's one other form of soil I want to mention. We don't have it in the continental United States because this is the tropical soil. The old name for it is called the laterite. Now, the old name, I might add, is still used the world round, but the new name for it is the oxisol. In the desert, in the tropical regions, what the soil is simply an intimate mixture of 3 oxides: aluminum oxide, iron oxide, and silicon oxide. Where are the clay minerals? There are no clay minerals. The intense weathering in the tropics is such that even the clay minerals, once they form, decompose. Now, that's going to form a little problem for us a little bit later when we start talking about using soils to support plant life. Okay, so there's just a basic idea of the fundamentally different kinds of soils. But note the important thing, it's a climate thing as to what kind of soil that you're going to get. Now, we have to talk about the clay minerals. Without the clay minerals, soils would not do their thing. So here's some information about the clay minerals. First of all, they are very, very, very special. They're different than any other minerals we've talked about. Because if you think back to our discussion of minerals, anytime you make a natural compound a mineral, or a compound in general, the big deal about it, a chemist will tell you, you have to end up with electric neutrality. The plus have to cancel out the negative charges. In other words, cations and anions have to balance each other out. So compounds are electrically neutral. All minerals are electrically neutral except for the clay minerals. Knowing what they were going to use for, nature saw to it that the clay minerals are never, and the word is never, electrically neutral. With rare exception, they are always negatively charged. Now, the problem is, though, there's still the law, thou shalt be electrically neutral. Well, the thing is, if you can't solve the problem on the inside, the only way you can solve it is on the outside. So here's the way it works. Picture this particle of clay negatively charged because there's not enough cations within the lattice. But here we have then rainwater percolating down through this soil. Coming along with it, there are things in solution, which means there's some kind of cation and anion, of course, but we're interested in the cations. So here comes the water down past this clay particle, negatively charged. And whatever that cation is, it simply goes over and it sticks on to the outside of the clay particle to neutralize that negative charge. How many cations stick on? It's just a function of how big that charge is. The bigger that negative charge is, the more cations stick on there. The lower the charge, the fewer. But the idea is we have taken care of the problem of neutrality on the outside by adsorbing cations. Well, we call that process cation adsorption. But here's the interesting point. The clay particle doesn't care who's out there. It doesn't care what kind of cation it is, as long as it's a cation. All the clay particle cares about is there are enough cations out there that take care of that negative charge inside. So, for example, let's say this particular cation is now surrounded by this clay particle is surrounded by cation A. Then it rains again, and somewhere along the line, the rain picked up cation B. So here comes cation B now down through the soil past this clay particle surrounded by cation A. If the cation B in solution is greater in concentration than the cation A on the clay particle, the cation B comes over and kicks the A off and takes its place. So now it's surrounded by cation B. What happened to cation A? It just went back into solution again, is going off wherever it was going before. So now we have B in cation exchange positions. But if another cation C came along, it could kick the B's off. If A came back, it could kick the B's off. So you see, it can exchange one cation for another, and that's the important part that the clays do. It's this ability to exchange one cation for another. That's what the clay minerals can do that no other mineral can. It is so important that the soils people have a test they run in the lab. They call it the cation exchange capacity, just called CEC. The cation exchange capacity. Some materials have very high cation exchange capacity, some have lower. That's what they want to find out. Why? That's what determines how much nutrient material that the soil can hold. Remember, it's supporting plant life out of doors. Supporting plant life means you got to feed them. This is where the food we're talking about is. It's adsorbed to the outside of those clay particles. The higher the cation exchange capacity, the more food this particular stuff can hold. The less it can hold. So that's why it's very, very important to them. Okay, now, you understand on cation exchange, very, very important. It can go on forever and ever and ever. Now, the next thing I want to do, I want to talk about some problems with soils. We were just talking a moment ago about different kind of soils in different areas in our gardens. Back where I come from, the problem in our soils, and this is generally true east of the Mississippi, wherever you have this high precipitation level, the soils are acid. Acid soils. Question, what does that mean, the soils are acid? Well, here's what I want you to do. Picture this again. Here you have these clay particles down there in the soil, negatively charged now. Whatever the cation is on there, I really don't care at the moment. But here we are, we're getting, let's say, greater than 20 inches of precipitation. Here where I live, we get greater than 40. So here we have the rainwater moving down through the soil. But remember now, this isn't just rainwater. This is a dilute solution of carbonic acid. Now, carbonic acid is a weak one. It doesn't like to dissociate, but it does. And there's some hydrogen ions and bicarbonate ions. So the dominant cation now moving down through the solution is the hydrogen ion. It goes over and it kicks off whoever happens to be there on the clay particle and goes in its stead. And so now the clay particle is surrounded by hydrogen ions. We say the soil has been hydrogenated. Well, so what? Well, note what I can do as a chemist. I could sort of write a little formula that represents each and every one of those little clay particles. And I would write it hydrogen ion +1, put brackets, write clay mineral in the brackets, negative. Note the clay mineral basically becomes the anion because it is. It's a negatively charged thing. So here we have a compound, H, bracket, clay. Well, one of the things you learn in chemistry pretty quick, in inorganic chemistry now, not organic, in inorganic chemistry, is that any compound that begins with an H is an acid. H2SO4, sulfuric. HNO3, nitric. H2CO3, carbonic. Anything that starts with an H is an acid. So that means this thing's an acid. Here's another definition for acid. An acid is any compound that will provide a hydrogen ion into solution. Well, no, let's say we have this clay particle there. It's got a hydrogen ion on it. The clay particle's the anion. Along comes another cation, cation X. I don't care what it is. It kicks it off. Now the hydrogen ion, where does it go? It goes back into solution again. Therefore, for another reason, this particle is an acid. Well, they're all like that. So if that particle and everybody else is an acid, the soil is an acid. So that's what we mean by the soil is acidic. Now, what's the problem? Well, I guess the problem is what you want to grow. Now, there are things that really like acid soils. And if you want to see what kind of things really like acid soils, just take a walk in the woods. All the things you see around you, Scotch thistles, common plantains, the grasses you see, anything you see out there growing naturally, they like those acid soils in this neck of the woods. So they grow all right. But that's not the stuff that you want to grow in your garden or in your lawn, you see. This kind of stuff that we want to grow usually doesn't like acid soils. They'll grow all right, but they won't grow very well. So what do? Well, the guy from the grocery, not the grocery, the place where you buy all the stuff for plants, he says he's going to neutralize the soil, all right? We got to neutralize the acidity. How do we do that? Well, what you do is you go down to your nursery man and you buy what they call ag lime. Okay? Comes in a bag. White powder. What is it? It's nothing but powdered limestone is what it is. Calcium carbonate. So here's what you do with it. You take it home, you spread it all over your yard, all over your garden, and in the spring of the year, you see this in the East especially, everybody's lawn is white and everybody's garden is white. That's what they've done. They spread this stuff out. It's powdered calcium carbonate. Why is it powdered? Well, one of the things you learn in chemistry, as the particle size goes down, the surface area goes up, and that's one of the things that controls all chemical reactions too. So here's the deal now. You've got this powdered calcium carbonate on the surface. It rains. Carbonic acid reacts with this stuff, puts the calcium carbonate into solution as calcium ions and bicarbonate ions. Now the carbonate ions are moving down through, the calcium ions are moving down through. The calcium ions now is the dominant cation in solution. So here you have this clay particle surrounded by hydrogen ions, but the calcium ions are concentrated more. They come over and kick the hydrogens off. Now this particle is surrounded by calcium ions. Now look at the formula. Calcium plus 2, bracket, clay, negative. Is it an acid? Doesn't start with an H. Doesn't look like an acid to me. Can it provide a hydrogen ion into solution? No, there's no hydrogen ion to provide into solution. It'll provide a calcium ion if you want it, but not a hydrogen. Therefore, the clay particle, you see, is no longer acid. You have neutralized the clay particle. Now you've neutralized the soil. Where did the hydrogen ion go? Well, it went off into solution, reacted with that bicarbonate, went back together, and formed undissociated carbonic acid, which isn't really acidic at all, and off it goes. So now you're ready to grow anything that you want. How are you going to do that? Well, I guess I could pick any kind of thing that I wanted to show you how this, and I'm not a gardener, but anyway, I want to pick something that all of us have tried to grow, a lawn. Now, we're talking here grass. Here's the thing about grasses in general. What grasses like to grow, like to eat, is calcium ions. They like calcium ions. So the deal is that here you have a lawn, let's say it's acidic. Grass will grow, nature's grass will grow, but the kind of stuff that you want to grow, the Scots variety, this green velvet lawn, they don't like those acid soils. So what do you have to do? Well, you have to neutralize it. So we've gone through now, we put down the ag lime and it's all neutralized and all the little particles have all these calcium ions around it, and the grass really likes that kind of stuff. So it sends down its roots, and now the grass wants that calcium ion that the particle has, and the question is, how's it going to get it? Well, it could say, well, clay mineral, why don't you give me some of those calcium ions? But it can't do that, because you see, if it just gave the calcium ions away, then it's going to have this negative charge to be reckoned with. So it can't just give them away, but it can exchange it. What is it going to exchange it for? Well, if you look at the roots of plants, what they do, they secrete carbonic acid. Carbonic acid dissociates into hydrogen ions and bicarbonate ions. That hydrogen ion is a cation. So the idea is the roots of the plants secrete carbonic acid, generating hydrogen ions that go over and exchange for calcium or whatever it is they want. They take up the calcium for their food. There's your nutrient, you see, and they replace it with hydrogen ions. And that's why your garden looks so good right after you lined it. It's beautiful because it's gotten all the food and it's doing really, really well. But note, over time, pretty soon, it will have gotten all the calcium that was down there. And so what you have to do, well, what you have to do is you have to replace it with more. So you see, if you want one of these lawns, then you got to go and treat it again. You got to put down more lime. And you got to do that all the time. And you see, I went through all this one time. I had one of those lawns. And the thing they don't tell you is that even when you do all that, there's all kind of things that attack these lawns. There's cinch bugs that eat off the roots. There's bacteria. There's all fungus. And then what do? You got to buy fungicides and herbicides and all. And I was doing that. And all of a sudden one day I said, Renton, you're a chemist. Why are you doing this? You're putting these things in the soil. And anything that ends in a side is like suicide. Somebody's dying. So I quit doing that. I just let mine die. And some other grass came in and took over, just the old field grass. No, is it not as pretty? It's green. I mean, crabgrass is okay. It's green. I don't know what this stuff eats. It doesn't eat anything I feed it because I don't feed it anything. So anyway, there's a little thing there. Think about it next time you want one of those green velvet lawns. So anyway, now you see how this works. Now, I want to talk about one other soil because this is probably the most important soil in the world for agriculture. Question, can these acid soils be used for agriculture? Can the soils in the East? Yeah, they can. You can drive around the East, you can see farms all over the place. But you've got to neutralize the soil first. You've got to get in there with the ag lime. So that's the reason why in the East, the ag lime business is a big money maker for somebody. But let's talk about that mollisol. This is a very interesting thing. The mollisol now, whenever you go with mollisols, you don't have to do that because here's the deal. We're talking about an area that's semi-arid to begin with. What that means is the equal probability times of precipitation and drought. You got two forms of water now we're dealing with in contact with this soil. You got rainwater coming down, which is acid, but then you've got groundwater. Now, we've talked a little bit about it. This is the water that's heading back to the ocean. Remember all the stuff that was being taken in as a result of chemical weathering? We're talking about those soluble bicarbonates. Those are alkaline things. So the chemistry of groundwater now is totally different from the chemistry of rainwater. So what happens is that during the rainy season, the water moves down, acid water. Maybe it puts the hydrogen ions onto the clay minerals. But then during the droughty time, the groundwater moves up through the soil, bringing along those calcium ions, which kick the hydrogen ions off and now replace them. Note, self-neutralizing? Yes. But what happens when it rains again? Why doesn't when the rain comes out, isn't the hydrogen ion going to kick off the calcium ion? No. Why? Hydrogen ion +1, calcium ion +2. +1s don't kick +2s off. So the idea of these mollisols then, the big difference between them, they are self-neutralizing. You don't have to treat them. When it comes to agriculture, which we'll talk about a little bit later, these are the great agricultural soils of the world because you don't have to do anything with them. They're all ready to grow, and they'll grow just about anything you want. Now, the question is, what is it they grow worldwide today? Well, I think I'll let that go until we talk about the individual soils and the structure within the soil, and we'll bring the subject back up. But that's for the next lecture.